understand the work energy theorem, over here the thing to understand is when force is applied, it can do work. It can do two kinds of work. One is if the center of mass is allowed to move, that is to accelerate, that is center of mass is free to translate, then this force can do translational work. Similarly, if the body is allowed to rotate about some axis, then this force can also do some rotational work. So work could be two types. One is rotational work, the other is linear work. So in an inertial reference frame, we say that is the work which is going to be done by conservative forces, non-conservative forces and other forces. That is, work C stands for work of conservative forces. Certainly the work done by conservative forces is done at the expense of their potential energy, and work done by non-conservative forces plus work done by other forces is going to be delta K, that is change in kinetic energy. Over here when we say work, this work includes the translation work as well as rotational work. Similarly over here when we say change in kinetic energy, this represents the change in translational kinetic energy as well as the rotational kinetic energy. Let's understand it by few examples. Let's take the case of a rod of mass m and length L, which is pinned at one end and it is free to rotate in a horizontal circle. It is not vertical circle, it is horizontal circle. It is uniformly massed rod, mass m, length L, and it is pinned over here and it is free to rotate in the horizontal circle. Now what happens is at one end a force F is applied which is perpendicular to this length, and this force is continuously applied in this direction only, that is perpendicular to the initial length of this rod. It is asked, that is, what is the rotational kinetic energy of this rod as a function of angle theta from the original. So we are looking from the top. Initially the force was applied over here at this end and this is always being applied in this direction. Now it has attained an angle theta. We are interested in finding what is the rotational kinetic energy of this rod. So dW is torque into d theta. It goes from, theta goes from 0 to theta. If we integrate both the sides, work is equal to torque. Torque is, it is F, if this is L, so this is L cos theta. At any instant suppose this is happening, so torque of this force about this axis, it is rotating about this axis, so it is going to be integral of, that is F into L cos theta. The thing to understand is as theta is changing, so this perpendicular distance between the line of force and acceleration, that is also changing, that is torque is also changing. So we cannot say that is torque is a constant torque, it is a variable torque, so that's why we have used integration. So FL cos theta, that is torque, and for small displacement, that is d theta, we can say d theta. This is the work of this torque in rotating the body through a small angle d theta. So that comes out to be obviously FL sin theta. This comes out sin theta. So this is work. And where it will go? It will go in changing the rotational kinetic energy, that is rotational kinetic energy final minus rotational kinetic energy initial. What is rotational energy final? It is half I. I about what? I about this end, not about this center. About this end we know, we have done it in when we had done how to find the moment of inertia of a rod about an axis passing through its end and perpendicular to its length. It was ml square by 3. So that comes out to be ml square by 3. So it is half I omega square. So this comes out to be FL sin theta is equal to this thing. So from here omega comes out to be 6f sin theta upon ml.